Welcome, welcome. Music of Blue Oyster Cult. Don't Fear the Reaper bringing us in a song that needs more cowbell, for those who remember. But you know what we don't need more of? We don't need any more enteric cow methane in the world. So with that, we're going to start off our methane removal event in Air Miners. This is a new event for us because to date, everything that we've done has more or less been centered around carbon dioxide removal. But we are, after all, air miners, not carbon miners. Thank you very much. So we are branching off into a topic that's spawned quite a bit of interest in our community in terms of removing CH4 from the atmosphere, which has the potential to be extraordinarily impactful for our climate. With that, we have a excellent panel today, and we're going to start off with a little bit of a different tack from what we typically do with Air Miners events. Usually we go right into discussion. Today, because this is a brand new topic for many in our community, Erika Reinhardt from Spark Climate is going to have a maybe 10-minute or so presentation on just a level set, because we all love a good level set, so that we can understand the terminology and sort of the landscape of what methane management looks like today. Then we'll go into a panel discussion with the illustrious Megha Raghavan from Open Air Collective and Carbon 13, moderating with Professor Matthew Johnson, who is at University of Copenhagen and also the CTO of Ambient Carbon in Denmark, and Erika as panelists today. Don't know, so we will go from there. And then at maybe 45 minutes in, we'll have our typical Q&A, and then I'll come on at the end. At that point, we'll stop the recording at the top of the hour again and have our networking afterwards in Zoom breakout rooms, so that we can continue to get to know each other, not just know of each other, and accelerate the pace of developing methods to remove methane from the atmosphere. So with that, I just want to say thanks again for coming, and event's being recorded and will be put onto our YouTube channel afterwards, and look forward to a very engaging discussion. So Megha, do you want to just take things away for a second?
Yeah, thanks, Jason. So like Jason said, I'm Megha Raghavan. I'm over at Carbon 13 working on carbon removal, but really excited to be here talking about methane, since I think it doesn't get talked about as much in the carbon removal community. So yeah, we're going to start with a quick presentation from Erika. Just I'll quickly introduce who we have on the panel today. So we've got Erika Reinhardt. She co-founded Spark, and she leads the organization. And her background is in leading product engineering groups at high growth software companies with an impact orientation after having studied engineering at MIT. We also have Matt Johnson, who is a professor of atmospheric chemistry at the University of Copenhagen in Denmark, and he has authored 134 research papers, 12 patents, and the textbook Chemistry and the Environment, published by Cambridge University Press. He's also founded a series of startups, including Infuser, Airscape, DevLabs, and Ambient Carbon. So Erika's going to start us off with a very quick presentation. I will then go through a few questions that I'll moderate with the panel. And then we're going to open it up, like Jason said, to questions from all of you. So please keep those questions in mind as we go through, and we'll get towards them in the last 20 minutes or so. All right, so Erika, whenever you are ready.
Great, thanks, Megha. All right, this is going to be a very quick introduction to methane and methane removal, and probably spark more questions than answers, but we'll hopefully have time for those after this. So very briefly, where we're at in overall climate situation right now is not great. Current climate policies and our trajectory is leading us to a 2+ degrees C world, where we know there's both major human impact risks as well as increasing Earth system risks as we exceed the sort of guardrails of 1.5 and 2C. There's a number of different Earth system risks that are of increasing probability as our temperatures continue to increase, and these are partially determined by the peak temperatures that we see. So methane is an incredibly important piece of all scenarios that keep us below 1.5 or 2C on top of achieving net zero CO2 emissions through a combination of both obviously CO2 reductions, as well as there being a really important role for carbon dioxide removal. What we see here, though, is that, the difference between only talking about CO2 here in blue and also talking about all greenhouse gases, where one of the big differences here is methane, really is the difference between being able to have any chance of staying in under these guardrails and absolutely not. The other key thing here to understand is that when we think about peak temperatures, which have an impact on natural system responses, that there's really two primary factors. It's obviously a lot more complicated than this, but there's two primary factors in that, and that is how much cumulative net CO2 we've emitted up until the point of hitting net zero, as well as what the rate of net methane emissions is at that point in time, as a pretty simple mental model. And so as we race towards net zero CO2 with the addition of CDR, it's also really important that we race towards as low of methane emissions as possible. So methane plays a much larger role in this system than most people realize. So, currently, if you look at where warming is coming from, about a third of it is from methane on a gross basis, about 45% on net basis, about 0.5 degrees today and growing. This number is probably closer to 0.55 or so by now. And you can see when we look at all of the different contributors to radiative forcing, that methane is here as the number 2 warming contributor, right after CO2. Methane acts really differently in the atmosphere, though, than CO2 does. So this top row here is methane, this bottom row here is carbon dioxide. And the key thing to call out here, which I think causes, probably different framing potentially for this group, is that stopping emissions of methane, as we sort of see in this portion of the scenario here, does actually lead to a reduction in atmospheric methane due to its short lifetime. This is not true for CO2, right? When we stop adding CO2, we stop adding to that sink, but there's not yet a drain, and CDR is the drain. Methane is unique in that there is a natural drain, and we'll talk about in a minute what those are. We see a role both for cutting methane emissions as aggressively as possible, which is on its own actually going to start to bring down these concentrations and the warming, and also to work to accelerate those processes to draw this down even faster. But methane does, because of its different interactions in the atmosphere, does have its kind of own cleanup mechanism built in. And so you could argue really that methane emissions reductions is a flavor of air mining, in that it is cleaning up the atmosphere. So just to sort of put this all together, this is a view of all the different climate forces. We can nerd about this for hours, but in very brief, this is the warming caused by different gases. And one of the reasons that methane is so important to address is that, as we just covered, the warming from CO2 here continues to be additive as we add more CO2, and it will only come down as we do massive scale CDR. This methane bar here has 2 opportunities to go down, hopefully, which we might be able to do in parallel to make it go down even faster, which is cutting methane emissions as well as accelerating the atmospheric methane removal. This is really important because what you see here is that actually we already have 1.5 degrees C. This is average of 2010 and 2019, so it's worse now, but even in 2010 and 2019 in the IPCC consensus report, we were already at 1.5 degrees C of gross warming in the atmosphere from greenhouse gases. And the reason that we've only been seeing about 1 to 1.1 warming is because of these aerosols that have been cooling us, but these will sort of be going away over the next few decades due to changes that we're making over here that are incredibly important, but really mean that these methane emission cuts are really critical. And that's why fundamentally, when we look at the climate models that keep us under these guardrails, that we are so dependent on methane. We're so dependent on this bar going down. The bad news is that we're not achieving that yet. So atmospheric methane levels continue to increase, and recently precipitously. And this is right when we know that these need to be going down dramatically in any of the 1.5 or 2C consistent trajectories that we see here in blue. You can see that there's a major step change needed here, that there's no evidence yet that we are successfully making. Methane comes from a variety of sources, both anthropogenic, which you can see here in the middle in red, as well as natural, as you can see here on the sides in this sort of green teal color. An important thing to call out here is that many of these natural emissions were pre-industrial, and we don't need to get all of this down to zero in order to return to pre-industrial levels. However, as we'll talk about in a minute, these natural emissions have evidence of increasing, and those elevated emissions are quite concerning. I'll talk about them more in a second, but the other big thing here to see is the sinks. So the sinks for methane are very different than CO2. They are mostly atmospheric and a little bit here in the soils. So if we look at just the anthropogenic piece of this is today the majority of the elevated emissions are these anthropogenic emissions. And what we can see here is that there's a huge role for R&D and innovation in order to develop more methane emissions technologies. All of the areas here in red do not have technical solutions yet. Those that are in orange are technically feasible, but come at some cost, variety of costs. Many of those will need to be brought down. And the yellow ones, that light yellow color, are basically cost neutral to do today, but still require massive policy and practice change support to actually happen. So in terms of people's entrepreneurial interest, any of these sectors here and any of these different flavors of types of work are all really crucially important for us reducing our anthropogenic methane emissions, which we need to do very, very urgently, and which fortunately there is increasing policy and market support to do. On the natural side, as I mentioned before, there are increasing risks of natural methane emissions increasing dramatically with really high uncertainty bars. This is coming from primarily permafrosts and wetlands. And right now, the real danger is that these systems can emit more methane as a result of warming and then further feed warming with large methane emissions increases. On the sink side, so all the things in blue here are different forms of atmospheric sinks. So there are a bunch of different atmospheric chemistry reactions that basically clean up methane and largely convert it to CO2 as well as water and a few other byproducts. Matt is the person you want to ask about all of your detailed atmospheric chemistry questions. There is also some in the soils. One thing that's important here is that these sinks do not naturally grow as methane emissions grow. And so the current lifetime of methane of about a half-life of around 12 years is dependent on these ongoing reactions, and they're very complicated, nonlinear, and dependent on a bunch of other stuff happening in the atmosphere as well. So the bad news is that when we think back to that graph of methane kind of going faster and faster, that there is recent evidence that this is largely driven by some of the most challenging to control sources, which are the natural emissions, in this case wetlands, as well as changes in atmospheric chemistry. And so we really need to get a hand on all of these portions: anthropogenic emissions, understanding what we do about natural emissions, and really understanding better these atmospheric processes that are currently doing this really important job of cleaning up the atmosphere kind of for us. So we think about this in terms of sort of different possible intervention points. So wherever and whenever we can, we absolutely need to be avoiding methane emissions in the first place. And just to use one example as an illustration, right, for livestock, that can mean everything from having fewer of them to changing their ruminant biological processes to be burping less methane. We categorize that all as methane avoidance. There have been targets set by the Global Methane Pledge around international and anthropogenic methane emission reductions that would capture this. There's a relatively emerging category, and this is one that Mann is working on, in ambient carbon, around methane emissions destruction. So once methane has been produced, are there ways that we can help to avoid low concentration streams from entering the atmosphere? You can kind of think about this as flaring, but for very low concentration methane sources that can't be flared. Flaring requires a pretty high concentration to just technically work. And then there's a separate category of atmospheric methane removal, which is to help address methane once it's already in the atmosphere. And Spark strongly believes that that should never be used in place of any of these other earlier upstream options, because in order to tackle this problem, we really need to be as additive as possible. And using removals to offset available methane emissions reductions isn't going to get us anywhere. Similar to CDR, if CDR's only role were as an offsetting mechanism, you wouldn't actually see a decrease in emissions, nor would you see any negative emissions capacity being built up. So why study atmospheric methane removal kind of at the end of that pipeline? It's potentially incredibly important for addressing near-term warming and peak temperatures, as well as helping to avoid and or respond to natural feedbacks, to help off-ramp from these methane emitting feedback loops. We also think it's incredibly important that just in general, and this is true for CDR and many other areas as well, that we be developing these additional tools that we may need in our overall toolbox as sort of the overall situation evolves. And part of that is learning what doesn't work as well as what does work, and getting to the bottom of that so that we kind of know what our options are. And so we think even if this work ends up resulting in fewer options than we are hopeful for, that will still be important to know. What we're also finding is that the research that you need to do in these areas ends up actually touching a number of other very critical areas that help to advance atmospheric chemistry and overall climate science, by really understanding the atmospheric oxidation, the oxidation capacity of the atmosphere, which is necessary to understand many of the atmospheric methane removal methods, but also just improving our understanding of what's already happening and what might happen in future emission scenarios, even without the potential addition of atmospheric methane removal approaches. So in building this field, I think there's a few really important things to really deeply understand and grapple with, which is that the only way we achieve our climate goals is by doing everything. And that means emissions reductions, both on the methane and on the carbon dioxide and all other greenhouse gas side, as well as we know there's an incredibly important role for large scale permanent CDR for helping to bring down long-term temperatures. And methane removal has a particularly important potential additional role in helping to address near-term warming on top of that. It's always easier to avoid emissions before we talk about removing them. And to the additive point, we really need to be doing both if we're going to get to where we need to go, which is mitigating overall climate impact. We also know that climate interventions that don't have social mandates can easily backfire if mishandled and need to be treated very carefully. And again, just like in CDR, very different methods need to be treated very differently, right? We're talking about a range, and we'll talk about in a minute particular approaches. We're talking about a range of approaches that might range from closed system interventions to open system interventions, and how we govern and incentivize and monitor them need to be different as appropriate. Just like in CDR, you govern DAC very differently than ocean CDR, for example. This is also an incredibly early field. We don't know yet what the potential scale of these solutions will be. And we think it's incredibly important that we not overpromise or bet on these solutions being at a very large scale, because there's huge downside to doing that if the solutions end up not developing in such a way that capacity actually exists if we're dependent on it. And so it's important to build the field in such a way that acknowledges sort of the wide uncertainty of future capacity. So as we think about where we need to get the methane removal field to be in the next decade or so, there's a few really important tenets. These kind of mirror those in CDR, but they're different. So obviously any intervention will need to be climate beneficial. It will need to be socially accepted, and that's a combination of understanding the full health, environmental and other impacts, looking at resource use, looking at local community impacts. We need to be able to verify and monitor what's happening. And we need this all to be additional. This is a little bit different than what you see in CDR, which has things like permanence really, up front and center. And that's just because the chemistry here is so different. We're not storing methane like you're storing CO2. It's really the values in this conversion that happens. And so we need to verify that conversion happened. And we need to understand any other conversion that may have happened as well, any of those side effects. But at the end of the day, once that conversion happened, there's less of like a storage or permanence type sort of factor here. And we then take that from the field scale to a looking at approach by approach scale. Again, just like CDR, we expect this is going to end up being a basket of approaches that are going to have different resource constraints and different factors in them. And so as we think about, okay, well, how do we judge basically these different approaches, particularly in their early research days, as they all are today, we're really looking at, is there a pathway to this approach being feasible, where feasible means cost plausible, climate beneficial, and also what would the scale of this possibly be, even in the best case? Could it play a really big role, or is this something that's always going to be really small? Really small things we can do too, but they're going to be prioritized differently by the ecosystem. And we do want to help support the approaches that are going to add up to the scale that we think is going to be necessary here. In addition to these criteria, they're a little bit less black and white, but we need to really understand all side effects, and that includes health impacts, environmental impacts, in order to be able to make sort of future holistic decisions around any deployments and make sure that we are always mitigating any potential harms that any of these methods may have. So this is a sort of quick way that you can kind of calculate this for the climate beneficial and cost effective feasibility constraints. You can do much modeling, and this work is currently getting done to really understand in future scenarios, we're looking at future energy mixes and other things that are changing between now and then. What would these things pan out, and what are the directions of innovation that would be required in order to get them to pan out? And we'll talk about in a minute for each of the different methods, kind of what the vectors are of the breakthroughs that are necessary in order to have them start hitting some of these criteria. So there are 4 different sort of high-level categories of how these things can be deployed. And so those are atmospheric methane filters, terrestrial methane consumption, surface treatments, and oxidation enhancement. We'll talk about these each in a second. I think the important thing here to note is that there is a variety here of both open and closed systems that we're talking about, as well as systems that are more passive in their airflow, or maybe would be active in airflow. And just a very different, energy intensity requirements. There's also different ways of kind of breaking down this field. So we'll just talk about kind of the rows as the categories today, but it's just worth noting that you can also sort of think about it in terms of the columns, in terms of what the fundamental chemistry is that's powering each of these reactions. And so sometimes as we look at one of, a type, we kind of think about, okay, well, then what are all the ways that can be deployed? Both useful ways of looking at it, too much to go into today. So really a brief highlight of different approaches. So atmospheric methane filters are closed systems. So this is sort of the most analogous you can think of as DAC in the CDR world. That's air flowing through them and some sort of catalyst or other reaction happening internally that is oxidizing methane. There are a bunch of different approaches to this. On each slide, you'll see there's some stuff that's bolded and put in red. These are the kind of like the really key innovation areas that are going to make the difference between these things being potentially feasible or not. So like we need to solve these red things in order for these solutions to be on the table, more or less. And so the summary here is, more innovation needed across many of these methods around achieving feasibility and also reducing the air movement requirements in terms of energy and climate costs. By making these systems lower pressure drop and or finding passive ways of moving air. The next category of approaches are surface treatments. These are currently all photocatalysts. And the really big question here is, how do we improve basically the efficiency, which technically is the apparent quantum yield of these photocatalysts by probably about 2 orders of magnitude in order to kind of make this area feasible. There's also in all of these areas, lots of questions beyond feasibility that we'll need to answer around side effects and many other things, but I'm just highlighting quickly the kind of key make or break ones here. Terrestrial methane consumption is really going back to those atmospheric sinks, looking at the soil sink, and so looking at, okay, how can we augment the biological processes that are currently a sink for methane. The challenge here is that these types of bacteria, methanotropes, grow very slowly at 2 ppm. And so the big question here is, are there strains that we can go find that are grow a lot more quickly at 2 ppm in order to have sort of relevant scale. And of course here ecosystem impacts are going to be incredibly important, as well as understanding the complex ways in which these bacteria can impact other greenhouse gases, particularly nitrous oxide as well. And then the final category is atmospheric oxidation enhancement. So this is looking at that really big portion of that pie chart, the 95-ish% of methane that is currently oxidized in the atmosphere, and looking at if there are ways of augmenting the oxidation capacity of the atmosphere, which would have potentially a very large impact on methane removal rates, as well as some other pollutants as well. The really key metrics here in terms of feasibility are really understanding the efficiency better, and Matt and his team are doing a lot of the research there as well. And any method that is touching the atmosphere is going to need to be deep science done around all of the side effects, be those environmental, health, etc. And so that's one of the biggest areas of necessary research in this space before being able to determine feasibility and desirability. Very quick overview, but here we're at the last slide. So just as a quick recap, atmospheric methane removal is very in its early research stages in order to help determine what methods may be feasible, scalable, and safe in the future. And all of those axes basically need more research and work right now in order to get this field to a place where we would even understand what the trade-offs we'd be making are. And as hopefully these methods are developed, they'll need to be deployed in really careful ways, both for social acceptance, as well as making sure that they aren't being used as trade-offs to other mitigation methods, be that methane avoidance or CDR and other areas, in order to really have the maximum climate impact here, which is never in replacing methods, but instead in adding them all up. And then on methane broadly, I think there's huge opportunity that's probably interesting to this group around on the methane mitigation side. There's tons of work to do there to actually bring those curves down, where we do have a lot more technologies that are ready to go or are probably fewer years of research away to being ready to be deployed and commercialized. So with that, I will stop this share, and I think we will move over to questions, of which I'm sure you have plenty.
Cool. So we have a couple of panel questions first that I'll go through, and then I'll hand it over to the audience. So yeah, just raise your hand or put them in the chat, and we'll try and triage them. Just quickly before I get into that, I think we've had David from Spark join us, which is great. So David drives science initiatives, and his background is in climate nonprofit advising, climate tech investment, and consulting, and he has got his PhD in applied physics from Stanford. So I think he'll be joining us as part of the panel, which is great news. I just wanted to start by talking a little bit about how all of you got into, this part of carbon removal, but also specifically, out of all things climate, how did you end up in methane? And maybe Matt, I will throw it to you first to kick us off.
Yeah, thank you very much. It's been an honor to be able to teach atmospheric chemistry and climate science for 25 years. And really get an overview of how things have been changing. And the one thing that has not changed is that carbon dioxide keeps going up. and methane keeps going up. And we look at the climate indicators and temperature continues to go up. And you could do two things with this. You could go into an existential depression, or you can do. And I think that the hopeful route here is that there are a lot of things that we can do. And I think it's people like this community who are able to bring these things into the world. And according to what Erika showed, if we follow this trajectory, we can bring this under control. There are some very real risks there. We need to avoid them. And I think methane really is the key to making that happen. So I'm very happy to be here to try to promote that message.
Great. Yeah, maybe David, how did you sort of come into working on methane and this particular topic?
Yeah, thank you. I think from our perspective, like it is and from my perspective, it's a given that we need to be doing decarbonization, more and faster and more aggressively and more broadly. It's an absolutely necessary part of the work. And as this community knows well, CDR is also necessary to layer on top. Now, CDR without decarbonization doesn't work, but CDR on top of it does really contributes a lot to long-term trajectories. But particularly as I dove back in to climate a few years back after taking some time in software, it was clear to me that there was sort of this focus on that long term to the exclusion of kind of the path that we take to get there, and the importance of sort of the path that we take and the importance of sort of minimizing peak temperatures, and a lot of the stuff that Erika walked through, and saw that on methane there was this opportunity to really explore what would be additive, particularly given the risks in the system, and particularly given the natural systems risks, which have just become, what would I say? If you look 10 years back, 15 years back, the thoughts around natural system feedbacks was that they weren't really going to be a factor until, much higher temperatures. And as we've learned more about the natural system, it's become clearer and clearer that that was perhaps too sanguine. And there's still a lot of uncertainty around it, but that uncertainty has been closed or is closing, and to a detriment. And so we saw methane as just an area that needed more focus given its potential impact, and with a mindset around how do we do this via growing the pie, growing the focus on climate, not taking focus away from any of these areas, but really sort of opening up a new front on this area. And we just saw so little happening relative to everything else. It just drew us in as a place where we could be the most additive.
Yeah, great. And Erika, what about on your end?
Yeah, for me, it was really looking at, where are the pieces of the puzzle that we're missing and where are the risks in the system that we're not yet able to manage, because those seem like areas that have generally been less at the forefront, and thinking sort of like a risk management portfolio and insurance mindset. Those scenarios seem incredibly important to start figuring out what tools we have. That was kind of my entry point into this particular field, largely just generally starting to grapple more deeply with the challenge of where we're at and what those impacts really mean for everybody, present and future.
Yeah, absolutely. I actually wanted to touch on something, David, you mentioned, and Erika, you presented a little bit about it, which is the idea of these tipping points. So maybe, David, you could start us off just talking a little bit about, what are they, kind of what would trigger them, and how much of like a binary sort of point is it really when it comes to some of the ones around methane?
Yeah, I'm certainly not there are world experts on this, and I'm not one. But what I'd say is, I think tipping point is a strong word. I like to think of them as sort of feedback systems, and as well as like sort of tipping elements. Many of these things aren't binary, There are binary moments in some of them as far as we can understand, but there is also uncertainty around that. They're both, there's a really good paper from, I want to say, early this year or late last year. There was an update to the earlier tipping points paper by Tim Lenton and some other folks. And I think David McKay is the first author on this most recent one, if I remember correctly. And it really lays out a number of these tipping points. Several of them do have specifically have sort of these methane emissions. It's interesting. A lot of people think about permafrost, which is one that has tipping like elements that happen at sort of that they believe happen at sort of these very large error bars, but that as early as 1.5 starts to see these elements of acceleration. Wetlands are not actually considered a tipping point, although wetlands are the largest source. Tropical wetlands are the largest source of non-anthropogenic methane emissions, and they do appear to grow with temperature. They just don't have a tipping shape, and so they're not a tipping point, but they are a feedback, and they are a feedback that is poorly parameterized and growing. There's a recent paper by Kleinen et al. That talks about this sort of potential underestimation of wetlands, and specifically in the current IPCC climate model, either the models that are used in the IPCC analyses. Thanks, Erika. There's a number of others. I think when you look at the Amazon, you look at these sort of forest systems, those also have tipping elements. Some of them aren't directly related to methane. That said, methane methane is such a powerful tool for that early warming. And we think about the sort of history system, sort of what it takes once we start to once tipping elements are starting to sort of come into play more, it gets harder and harder to move us back to a stable system. And methane, again, can play a role that is different from CO2 because, as Erika really well laid out, reducing methane emissions actually cools. It doesn't just stop warming. Not even talking about methane removal yet. Just reducing methane emissions has such a huge power. But being able to layer on top of that, methane removal could potentially avoid some of these nonlinearities in the system. I can list them if you want, but they're many and varied.
Yeah, no, I can imagine it's not a simple answer. Matt, did you want to add anything to that?
Yeah, I think there's been a lot of thinking about carbon dioxide, and we've known for 40 or 50 years how to remove carbon dioxide from an airstream. And I think the general public just really doesn't appreciate methane to begin with, but also how different it is chemically from carbon dioxide. And carbon dioxide dissolves in water. You can make salts out of it. You can make minerals out of it. And methane is very non-reactive. Chemically, it resembles a noble gas, and it's the least reactive of any hydrocarbon in the atmosphere. And this means that if you look at trying to remove it, you have a very different set of constraints than you have with carbon dioxide. Of course, if there's enough methane, you can burn it. It's a very good fuel. And the United States has been able to reduce carbon dioxide emissions by changing from coal to methane. That's fine. But there's a very long distance from when you can burn methane to ambient methane in the atmosphere. And that spans from 2 parts per million, the ambient concentration, to over 40,000 parts per million. And there we don't have very good technologies because you can't just trap the methane and up concentrate it. And so really your only choice would be to prevent it from being emitted to the atmosphere to begin with, or to destroy it. And so I think people just really need to start thinking differently when we enter the world of methane.
Yeah, it's a very different, like chemically, but also the concentrations, the warming potential and everything. And it's hard to sort of make the shift mentally a little bit. Just thinking about the commercial side a little bit, and maybe Erika, this is one for you as well. Can you talk a little bit about the business models and how that relates to the policy space? So I know in CDR, we're always thinking about the fact that the industry needs policy support to reach scale and to sort of get to a point where it's impactful. Is that going to be true with methane as well? And are the policies that are being written around carbon removal going to encompass methane, or does it kind of need a separate policy regime?
Yes, I think it's worth splitting out methane mitigation and atmospheric methane removal here. So, on the methane mitigation side, we're still also in very early days. Methane mitigation hasn't been a top of the policy conversation for as long as it has been on CO2. We are seeing, early important progress there. And I think the really key thing is starting to value methane emissions reductions. And so in the Inflation Reduction Act, for example, just passed last year, we saw the first methane tax put in place. That is an oil and gas specific regulation, but it does put a high price on methane, basically, equivalent roughly to the current social cost of methane. And that was a first, that we had an explicit tax on methane emissions, even from a single sector. So I think it's going to be a combination of both carrots and sticks that create markets where either because of regulations, companies are just forced to be deploying solutions that are reducing methane, or are being incentivized to do so or disincentivized from not doing so, depending on whether it's a tax or a credit, to really put a value on that, and sort of from that, then you'll have the downstream impact of more business models making sense and investment flowing, et cetera. And then we have to separate it dramatically from atmospheric methane removal, where some of those same structures might not be appropriate because they could come at the cost of methane emissions reductions if it's from an offset type mechanism, again, like we've seen in CO2. And I think there it'll be really important, going back to the point around different governance for different flavors of methods, to understand what is the shape of the thing that we're talking about and what are the appropriate ways of deploying that thing. And we'll see how that develops. We don't even really know how that will develop yet in CDR. In CDR, right, we're seeing incentives that are mostly going towards more closed systems, and we don't yet have broad consensus around how we might sort of judge and make deployment decisions around more open systems. And obviously that's more of a binary than it actually is. It's all a little more grayscale, but those same questions are going to apply to methane removal. And so any sort of deployment related policy is going to need to be grappling with what is the specific thing that we're talking about. So our work right now is largely focused on helping to understand what are the things that are on the table in terms of where the research shows that some of these methods may be feasible, so that we can have those informed conversations over time.
Great. Well, I know we have lots of audience questions, so I'm going to do just one more quick fire. I just want like one sentence from each person. So what do you think is the biggest barrier right now to scaling things up on methane removal, whether that's tech, policy, human capital, absolutely anything? Biggest worry and what you think needs to be done about it. David, you first.
Again, I think you have to break it into two pieces, and I need to have one answer. So on atmospheric methane removal, it's actually just fundamental science. We don't even know if it's a viable solution yet, and we need to spend. We have real work to do on that.
Okay, great. And Matt, on you next.
Yeah, I definitely agree. The technology readiness level is so low with this, and there are so many low concentration sources of methane, and so I think it's a huge problem, but it's very early stage, and there are significant challenges that need to be overcome before anything would be scalable. So I think we're definitely very early days.
Okay, and Erika, and maybe also a solution if you have one in mind.
What was the solution part of the question?
Just, what's if you have a particular barrier in mind, what kind of needs to be done to just quickly address it and get us
Yeah,
past
I
it?
mean, just to add on to their answers, I think it's focused research efforts with significantly more funding in order to support the parallelization and scale up of the research work. And so the solutions there are growing the funding pools, both philanthropically and from government, aligning and organizing the research community to be most focused on the questions that are going to move the overall field forward the fastest. But without solution development, there's nothing here really.
Yeah.
About.
Absolutely. Okay, we're gonna do some audience questions now. So use the raise hand button if you can. And Ryan, I'm gonna turn it over to you first.
Oh, thank you. Hi there. Thank you so much, Erika, Matthew, and David for the discussion. This is an exciting topic of which many of us are eagerly waiting for more progress. My question for you, I had two. I'll focus on maybe one that we didn't touch on as much, which is methane detection. Can you speak to the role that methane detection, both satellite-based or more localized sensing, will play in propping up the market environment for the solutions that are ultimately going to address methane on the eradication side?
I'm happy to take this one, Matt, unless you want to.
Yeah, go ahead.
Yeah, so I mean, the methane detection efforts that are ongoing are incredibly important. They are largely focused on anthropogenic emissions, and in particular are really good at detecting very high concentration sources, right? So they're like excellent at oil and gas leaks, not as excellent on distributed livestock, for example. I think they are going to play a really important role in a few different ways. One is to make visible what is currently invisible, to help increase our overall ambition here and help point out where these leaks, in particular on the oil and gas side, are occurring so that they are addressed. The other thing we didn't touch upon is that because of the many fundamental differences between methane and CO2, methane mitigation has been, methane monitoring has been a much harder problem. And methane estimation, because you're really always dealing with either a biological process, which has really high variability, or leaks, which also have very high variability. So if you go back to that IPCC graph I showed with like the anthropogenic stuff in the red in the middle and the natural stuff on the naturals on the teal on the side, you may have noticed those bars had like a solid portion and then a kind of transparent portion. Those are the error bars, right? Huge uncertainties. And unfortunately, we've been finding as we do more and more monitoring that the news is normally bad. Normally, people have found ways of underestimating their methane emissions in their reporting. And so I think what we're unfortunately going to see is that there are many, that the scale of the problem is larger than it's made out to be in many of these sectors. And it will also make it more visible so that we can regulate it better, we can react to where there are or leaks or other sources better, and just get a better handle on the exact shape of the problem, which is just weirdly hard in methane as compared to CO2.
I could just add quickly that I think the monitoring strategy needs to match what it is that you want to detect. And of course, there are satellites that can see methane, but they have a very low resolution. So 1 pixel would be many kilometers, and it wouldn't help you to identify a specific leak. But we have students who are going into different places in Denmark, like a wastewater treatment plant, and we're seeing 300 or 400 ppm of methane just within the plant where water is going around and things are bubbling out of the waste stream. And I think this is very common also on farms. So in a pig barn, we're also seeing several hundred ppm of methane. And so I think that if we had better low-cost sensors for methane, a lot of these operations would be able to better control their own processes. And right now, they just have no idea, where there are leaks, what stage in the process is producing methane. And so I think with time, as technology develops, we'll be able to get a much better picture of that. But low-cost methane sensors are definitely a priority.
And to add to that, a lot of the natural systems are not particularly well monitored right now. It's relatively expensive to do it in small-scale research projects. Some of them are in very inaccessible places, currently inaccessible places. And as a result, Erika was talking earlier about the sinks of methane. Well, the error bars around the sinks are actually quite large as well, because the error bars around the sources are quite large. And so we're doing a lot of, the global methane budget is full of very large estimates. And the team does an excellent job, but when you look at top down versus bottom up, there's actually quite a discrepancy right now. And that really impacts the certainty with which we can talk about what is anything actually doing. And when we, the additionality of methane mitigation, future methane mitigation work, and as well as, contemplating any type of eventual tests of if anything proves feasible on the atmospheric side, what is it doing? Well, you need to have better baselines for all of that as well. And that comes at not just measuring methane, not just measuring the sources, but also measuring how the sinks are functioning in different places. And all of this is currently under measured. So to answer your question very briefly, it's incredibly important.
Thank you all.
Yeah, sounds like a real challenge. Can we get Julia next to ask her question?
Great. It's really exciting, the breadth and depth of the work that's been laid out here, that's being done. That's very exciting. And Erika, you started out first with talking about the emergency and the tipping points and the guardrails that must be put in place near term. And I'm wondering, I'm really curious, what are your, of course, imprecise calculations on how many years do we have before we go over that tipping point?
Yeah, I don't think about it that way. I don't know if Erika wants to answer the question or wants to answer it differently, but I like to think of it as every fraction of a degree matters. And there's enough uncertainty in the system, and there are few enough, as far as we can tell, it's not like hard binaries, but things do get harder as time gets later, there's no doubt. But the framing of there's incredible urgency, and also we can't really know, right? And so we operating like we still can have, are still agents, no matter the timing, is sort of important, but that every moment that we act matters. I don't know if you'd answer the question differently.
I in no way, feel like it's hopeless. I mean, look at what's been put forth on this call. I'm just saying, have you done calculations that say, well, we don't have 25 years, maybe we have 10 years.
Yeah, I guess, again, the way I think about it is, if you frame it as how much time we have, it both leads to delay and sort of a near-term delay and then long-term hopelessness. And so we don't actually think about it that way. We try to talk about it as we're acting now. We need to act more and more and more, but we need to act without skipping steps. That Erika laid out, because there are, if you act before a technology is ready, or act before there's the right frameworks in place. So it's got to feed every part of the system. But in terms of like detailed calculations, no, almost not on purpose, right? We leave that to the folks who are looking at those systems a lot more detail than us, and I'll obviously consult with experts in different areas.
Yeah, and everything that I've heard on the call, this is so inspiring. Thank you.
Yeah.
Thanks, Julia. One last one, I think, before we're going to have to turn over. Roger, could you go ahead and ask your question?
Thank you. And I want to thank Erika for a fantastic presentation. My question relates to the economics of methane removal. So I understand that the science and the technology are really in their infancy. But from a public policy point of view, policy making is not an unlimited resource. So it would be helpful to understand at least, in rough terms, or in terms of, technical best case scenarios, what are we talking about in terms of dollars per ton of CO2 equivalent for methane removal potentially? Could it ever be anything less than in the several hundreds of dollars per ton of CO2e, or more or less?
Yeah, so it's a great question, and this is probably not the black and white simple answer that you're hoping for. So I mean, the there is certainly a possibility of some of these methods developing to be low cost relative to the social cost of methane. We think it's too early to sort of have any definitive numbers there, and a lot of the fundamental research that's happening right now is working to try to constrain that to get a sense of where we're talking about. But the most promising methods do seem like they have the potential to be far lower than lower social cost of methane, which would the equivalent for CDR would be much lower than the cost of CO2 and be under that sort of $100 a ton metric. We think it's important that we don't think about it as a replacement to CDR, and so we don't think CO2 isn't the most valuable metric here. And that's really going back to because methane and CDR have such different roles in the system. And so we see the role of methane removal being really focused on near-term warming to help keep temperatures down. And hopefully while in parallel, we are scaling CDR as much as possible. If we end up having both of these solutions at a massive scale, fantastic, right? We'll do them both. But again, it's far too early in the research to know from a cost point of view what any sort of economic driven decision is. And we also think there'll be considerations beyond the economics that will drive that eventual decision making.
Thank you.
Perfect. Guys, thank you so much for all the really insightful questions, and to our panelists for the extremely insightful answers. And I'm just going to hand us back over to Jason for sort of a little closeout and talking about breakout rooms and things like that.
Awesome. Awesome. Thank you, Megha, for an excellent job moderating today. And thank you to Erika, David, and Matt for your time today. We really appreciate it. It's a new and quite early stage field, as much as we think that carbon removal itself is early stage. Methane removal is even earlier, and which makes it really exciting. We unfortunately are not able to get to everybody's questions, and we are so sorry about that. But I did share the speaker emails in the Zoom chat. So if you have questions for Erika, David, Matt, or Megha, feel free to use those emails. I also shared a link for you to answer our post-event survey. What do we do well? What do we not do so well? The only way we can make our events better to serve you, our audience, is to hear feedback, good, bad, indifferent. We want to hear it so that we can move things forward. From this point on, I also shared a link to the Investor Academy. If you are an accredited investor, then Investor Academy is for you if you want to learn about what carbon removal is from the ground up. And that's going to happen on June 1st. So feel free to sign up for that. And keep your eyes peeled for another event that we are going to have in a couple weeks. Still working out the exact parameters for that, so stay tuned.